Feeling like taking a coffee break? So do I. What about we talk about Valhalla, the project that plans to bring value objects, user-defined primitive types, and universal generics to the Java platform. First of all, what is Valhalla? The project Valhalla is developed at the OpenJDK and has been under work for several years now. Early access versions have been made available on the OpenJDK website, and we just had one published the 7th of November. So that's probably the right time to talk about it. What is Project Valhalla about? Well, if you read the welcome page of the project on the OpenJDK website, link down below, it tells you that Valhalla is about augmenting the Java object model with value objects and user-defined primitive types, complemented with changes to Java generics. And it talks about performances. The goal is to combine the abstraction of object-oriented programming with the performance characteristics of simple primitives. There are 4 distinct feature sets currently under development. Value objects, and we are going to see what it is precisely, because this is what this early access build is about. User-defined primitive types, classes for the basic primitives, and enhanced generics. Valhalla already delivered several JEPs. In a JDK 11, it delivered nest-based access control and dynamic class file constants. Then it delivered the JVM constants API and hidden classes in a JDK 12 and 15, and warning for value-based classes that was in the JDK 16. As you can already see, Valhalla is not for the faint of heart. It's very technical, very complex, and sometimes maybe a little obscure. Maybe you never heard about these JEPs before, apart from the warnings for value-based classes. Indeed, these features do not have much impact on the code you write, at least less impact than the introduction of records or the new switch expressions. But they were still needed for the future elements that Valhalla plans to release. What is the impact of object-oriented programming on pure performances? Well, let us see that on an example. Suppose you have a list of city objects, and suppose that city is a record, and there are 2 interesting components in this city records, a population and a land area. And suppose that population is itself a record, with only one component, population, which is an int. And the same for the land area. Suppose we have another record called land area with one component, land area, which is a double. What you need to compute is the global density of these cities. Easy enough to compute, just sum all the populations, then sum all the land areas, then divide the global population by the global land area. This is your density. How can you write this simple algorithm? Well, there are actually several ways of writing it. Let us examine some of them and let us see how performant they are. First solution, without any object. Suppose you have your populations in an array of ints and your densities in another array of doubles. Well, there are still 2 ways of writing this. The first one is one loop for the population, something like this, and a second loop for the land area. And at the end of it, all you need to do is to divide the total population by the total land area. But you can also choose to write it in that way, with just one loop, and compute both the total population and the total land area at the same time. That's interesting. Which one do you think is more performant? Many people would probably choose to handle their computation in one pass over the data, right? Well, there is only one way to find out. Let us run the tests. Actually, computing this with 2 loops is faster than in one loop over your data. Be careful because it may depend on the size of your arrays. Here we have about 400 cities in our array. But once again, when it comes to performances, measure, don't guess. What about computing the same stuff with objects? That would give meaningful names of these ints and doubles, and we have records to do that. With them you can write much better code, more readable, a code that will explain what it does. How does it compare to the previous version? Well, that's precisely the problem. Not too well. Compared to the primitive type-based versions, it's almost twice as slow, which is a lot, and a bummer. Maybe this kind of difference is not really a performance hit on your application on the overall, because you have database access or some web access that will be much slower, but in some cases it may still be annoying. And the real problem is that it pushes you to write ugly code for the sake of performances. This point is exactly what Valhalla wants to address. Valhalla wants to give the performances of the ugly array-based primitive type-based code to the object-oriented code so that you do not have to choose between performances and readability. We are just going to add one keyword to the declaration of the population and land area record, which is a value. This makes them value records instead of regular records. Bear with me, you will see what is the exact difference between a value-based class and a regular class in a minute. But first, let us just take a look at what it changes performance-wise. Let us run the exact same bench, but this time with two value records instead of classical records. 230 nanoseconds, better than the one-pass version built only on arrays and primitive types, and close to the two loops version. Now, that's exactly what we wanted, and that's awesome. But wait, because Valhalla can do even better. Suppose that you have an array of simple ints, no object at all, and you just want to sum them. Let us compare the performances of this pattern with the one you want to write, which is an array of population objects, because you want to use meaningful types in your code. So this is the code you want to write. Unfortunately, the price to pay is real. You have a performance hit, which is the following, about 25%. And actually, this hit can be even much higher than that. But if we make this population record a primitive record, just like that, then the performance becomes much better. In fact, it becomes the same as the one with the array of primitive ints. This is the kind of performance improvement you may expect when Valhalla makes it as a final feature in a JDK. Where does this magic come from? Well, as usual, there is no magic, just some awesome technology that is doing wonders behind the scene. This is the main idea of Valhalla. Barely any change in a programming model, just small declarations here and there, a fair understanding of the consequences, and let the JVM do the rest. Valhalla introduced two new notions, the concept of value-based classes, or value objects, and the concept of primitive classes. You can already play with primitive classes with this early access release, but its main point is value objects, so let us focus on this one. We'll talk about primitive classes another time. So, what is a value object? Simple, an instance of a value-based class. Okay, so what is a value-based class? Simple. A class declared with the value keyword in front of it. On this example, it's a record, which is compiled as a regular class, so everything is fine. What are the constraints on value-based classes, and what can you expect from them? Well, this is the point where things become a little complicated. The first thing you need to understand is that an object in a Java language has an identity. This identity is used to compare objects with equal, for instance. It is also used to synchronize a block of code, and handling this identity has a cost. Each object has a header that consumes memory. When you create an object in Java, what you get is a reference to a piece of memory that has an identity. Suppose that you share a population object with other objects in your program. And after that, you decide to increase this population object that you shared. Of course, what you expect is that all these other objects are going to see this mutation. This works because under the hood, what you have really shared is a reference to a single piece of memory that everybody sees. So if you mutate the content of this piece of memory, then everybody sees this mutation. All this is fine, but it has a cost. Suppose you have an array of such population and you want to compute the sum of them. Because what you have is in fact an array of references, you need to read this reference to get the value you need. Reading this reference is a performance hit. On this simple example, it was about 25%. It may be in fact much higher. So the first optimization that may come to your mind is, oh, but why can't we get rid of these objects, inline them in the array, and get this performance back? Sure, you can try to do that. But then what about the references you shared? Do all the methods you shared them with need to update their own reference to still see the right piece of memory? That's not going to work. You need another solution. So let us go back to the beginning. Why did you share this reference in the first place? Precisely because this population object has an identity. Using this identity, you can compare these population instances with equal, you can perform some synchronization, and you can mutate the value of your population object. What about you give up this identity? It means that you cannot compare objects with equal anymore. Is that really a problem? Well, maybe you're not using equal. It also means that you cannot synchronize on that object anymore. But maybe you don't need that anyway, so that's probably okay. And it means that you cannot mutate your object anymore. That's a real constraint, but if you're already using records, for instance, and you should definitely be using records, you're already living with this constraint. Giving up this identity means that you are moving from a world where what matters with object is its address in memory, that is the value of the reference you have on it, to a world where what matters is the value this object is carrying. Moving from one world to the other is very tricky. Valhalla does it in two steps from this world of references to this world of values. The first step is value-based classes and value objects. This world is still a world of references, but without identity. It's an intermediate step to the world of values that is in fact needed. So what matters in this intermediate world is the value carried by this object, but you still have references. And the second step is the world of primitive types and primitive classes. Only values, no more references. You can already play with it with this early access build, but as I already said, it's not its main focus. So we'll talk more about this another time. Value-based classes are about giving up identity to get better performances. In many cases, you are not using this identity, but you are still paying the cost of handling it. So let's get rid of it. Instances of value-based classes are value objects, and there are several constraints with them. First, you cannot mutate them. Second, you cannot use them to synchronize blocks of code, so no synchronized instance method in a value-based class. And third, when you compare them with equal, what you are actually comparing is their fields. The classical regular classes are now called identity classes because they have an identity, and you can actually declare them explicitly with the identity keyword. What about abstract classes and interfaces? Well, in fact, you can declare abstract classes or interfaces as value abstract classes and value interfaces. And the same for identity. You can have explicitly declared identity abstract classes and identity interfaces. There are two rules with them. First rule, a value type, class, abstract class, or interface, cannot extend an identity type, class, abstract class, or interface. And second rule, a type, class, abstract class, or interface, cannot extend both a value type and an identity type at the same time, directly or indirectly. So for instance, a class cannot extend an identity class and implement a value interface at the same time. This is forbidden. In a nutshell, the value type world is isolated from the regular identity world. So the consequence is that a given class cannot have both identity classes and value-based classes as subclasses. This is not possible. But then, what about the object class? Because everybody extends the object class, both the value-based classes and the identity classes. Well, the object class is a special case. This class supports both identity classes and value classes as subtypes, but that's the only one that does that. And there is one rule. If you call new object, then what you get is always an identity object. But wait, don't you have this rule in Java where every constructor calls a constructor from its superclass all the way up to the object class? Implicitly, every object that you construct calls in fact new object. Well, precisely, value-based classes do not follow this rule. Implicit calls to superconstructors or explicit calls to super in the constructor of a value-based class are forbidden. Creating a value object does not call any superconstructor. And this brings several constraints on value abstract classes. First, value abstract classes cannot have any instance fields. That excludes inner abstract classes within an enclosing instance, because these classes have an implicit instance field to carry the reference to this enclosing instance. Second constraint, value abstract classes can only have an empty constructor that takes no parameter and with an empty body. And third constraint, value abstract classes cannot declare any instance initializer. And if you don't know what is an instance initializer, that's perfect. Never use that anyway. All this gives opportunities to the JVM to perform amazing optimizations. In fact, some of them were already in place where the JVM could see that the identity of a regular object is never used. As usual, download this early access build, play with it, and provide feedback on the Valhalla mailing list. All the links are in the description down below. And with this, I'm out of coffee. So that's it for today. Talk to you soon.